So today we start the third part of the substantive analysis of spatial point patterns, of spatial data, I should say. After the point patterns, the geostatistics, now we deal with discrete spatial data. And this is actually very different from before. With the point patterns, we dealt with events and the locations of events, and that's it. We never really went into the marked point patterns. With the geostatistical analysis, we deal with a sample. They're also points, but it's a sample from a continuous surface. So the purpose there is to use the information collected at those sample points to predict the continuous surface. In this spatial autocorrelation part, we're dealing with what we call lattice data or discrete spatial data, which is very different in that the sample is the population. The points that we observe, or the aerial units that we observe, are the only ones to be observed. So if you study rainfall in counties in Illinois, you have all the counties in Illinois. The counties in Illinois are not some kind of event that may or may not happen. They're not a sample from a continuous surface of counties. They're it. And so there is a different statistical framework needed to analyze data like that. But it uses very much the same concepts we've seen before. The notion of stationarity will come back because we need an equilibrium in order to analyze cross-sectional data. And we'll operationalize this concept of spatial autocorrelation in a slightly different way. With the point patterns, we encountered it when we dealt with the second order statistic. The K function was really, we didn't really call it that, but it was some way of measuring spatial autocorrelation between events. It was connected to the second moment of the point pattern. In the geostatistics, we modeled spatial autocorrelation through the variogram, the semi-variogram, and then its flip side, which we call the covariogram, which showed us how covariance between two locations changed with the distance that they were apart. Now we're going to define spatial autocorrelation in yet a third way, a different way, as it pertains to a collection of discrete spatial objects. I don't like to call them lattice data. That's the term used in the literature because then you think of a grid, and it doesn't have to be a grid. It can be irregular data. It can be points, as long as these points are discrete events. And just to give you an example of the points in one of the assignments, the centroids were used of entities in Puerto Rico. And I said, yeah, that's fine. You can act as if this is a point pattern. But it's really not. It is a collection of discrete locations. So now we can analyze these points and the values that are attached to them and see whether these same concepts we had before, spatial randomness, clustering, dispersion, whether these concepts pertain to the pattern that we observe for the data at the points. And that's what we'll do today. We'll focus on some of the basic concepts. I'll elaborate, and a lot of this is a repetition of what we had before, the null hypothesis, the alternative hypotheses, and then we'll get into specifics. First, fairly conceptually, what is a spatial autocorrelation test? There are many different spatial autocorrelation tests, but they all have things in common. What is it that they have in common? That's what we'll deal with here. And then I'll spend a little bit of time on an important concept that makes it all work, the concept of spatial weights. In point pattern analysis and in the geostatistical analysis, we use distance as the measure to get it all to work. We organize the squared differences between pairs by distance that they were apart. These G and F and K functions were all plotted against the distance that the points were apart or the events were apart. Now we move away from that because we have a fixed set of discrete locations. We use a different concept to get at this notion of spatial autocorrelation. And I'll just deal with the basic about spatial weights today. In the lab on Thursday, we'll elaborate this further and see how you can actually construct these weights in Geoda and in R. So let's start with the concept, and here I like to make a distinction between three notions that you see in the literature, sometimes used interchangingly, and they really shouldn't be. And it's important that you know the distinction. And we start with the concept of spatial dependence, then I'll get more specific with the notion of spatial autocorrelation, and then I want to say a few words about this word spatial association, which is, you see a lot in the literature, and it's an easy one to use, but it's also a confusing one because it's not clear what it necessarily means. So that's something to watch out for. We start with spatial dependence, which is the most formal one. If you remember when we talked about the concept of stationarity, we were really thinking about a property of a multivariate joint distribution. And one of the ways we thought about stationarity, say, in a geostatistical context, is that if we take one subset of the data, we can characterize that by a distribution. If we move this to another location in the data, the distribution has to be the same. That's the stationarity. Now, this distribution is multivariate in the sense that it is the joint distribution of all the events, or the joint distribution of all the observations that matters. So when you have a joint distribution, one characteristic of such a distribution is that the individual pieces are independent. In other words, when you have each individual, what we call marginal distribution, say what we observe at each location, we can simply multiply it together, and that gives us the joint distribution for all of them. That is the classic case of independence. We're not interested in independence. We're interested in the opposite, where that is not the case. So where the joint multivariate distribution of all the observations does not simply factor out in the individual marginal distributions. So it's very important to refresh these concepts if you're a little rusty in it. I think we talked about this earlier on, this notion of a joint distribution versus a marginal distribution, and then a conditional distribution. The conditional distribution is where you model the uncertainty in an event, or the uncertainty of observing certain values, given that you have some other information, conditional upon some other information. So that's always going to be better in the sense of you knowing more than a pure marginal distribution, which is just modeling the uncertainty of an event or of a value without knowing anything about the rest. And then the joint distribution models everything together, the uncertainty of all the values everywhere taken together. So spatial dependence then means that this joint distribution does not factor out. That's dependence. I'm not here. Oh no, now it's going to be. Wrong number? I thought it was for you. Okay, the dependence, where does it become spatial, is because there is a spatial structure to the way that it is not independent. And that's, of course, highly abstract. And also, this is primarily a mathematical device to prove theorems, to get at properties of tests and estimators. Because, we talked about this before, you never really observe a distribution. A distribution is a mathematical concept to summarize the uncertainty. Like a Gaussian distribution, you have this equation with e to the minus and so on. So that describes uncertainty. It tells you what is the probability that you observe certain values, how likely is it. But we don't actually see the distribution. We can estimate it, but we can only estimate it if we assume a particular mathematical form. If we say we don't know anything, we don't assume this normal or Poisson or binomial, how do we know what the distribution actually is? And it's not a practical thing, it's a conceptual thing. It's something that you use in the mathematical part of the discussion. What you want to get at is something that you can actually estimate. So, like we've done with the semi-variogram. Okay, that is something, we have some data, we get this semi-variogram, that tells us something about the spatial autocorrelation in the data. The spatial dependence as such doesn't really tell us what is going on in the data. And to get at that, we use the notion of spatial autocorrelation, which is specifically a moment, a characteristic of a distribution. So we talked about previously, say with the point patterns, about the first moment, which was the intensity, then the second moment was a measure of variance and covariance in the pattern. Similarly here, we will talk about, remember this is the joint distribution, we will talk about the first moment, which is the mean, or strictly speaking, the expected value at each location. The second moment is the variance-covariance matrix. Because it's a joint distribution, we need not only the variances at each of the location, but all the covariances between all possible pairs of locations. So that's a matrix. And the fact that the off-diagonal elements, what that means is anything that has to do with non-identical pairs. The diagonals are about the variances. The off-diagonals are about the covariances. When the off-diagonal elements are non-zero, then we say there's correlation. Where does it become autocorrelation? It becomes auto when the variable that you're looking at is the same in all locations. So instead of correlating, say, crime and income, we are correlating crime and crime. But it's crime in one neighborhood with crime in another neighborhood, for example. That's the auto part. And the spatial part is that the particular pattern that we see of these non-zero off-diagonal elements has something to do with spatial structure. And specifically, as we'll see later on today, it has to do with the structure of the spatial neighbors, and that neighbors are correlated. So then from a practical point of view, this is something that we can actually estimate from the data. And that is what we'll see later on today, a spatial autocorrelation test, or a spatial autocorrelation coefficient that we estimate from the data, and then based on that information we can decide, and this gets back to our usual framework, is this spatially random or not? We reject spatial randomness, then which is it? Is it clustered, dispersed, or as we'll see, positive or negatively spatially correlated? So, big difference between spatial dependence and spatial autocorrelation. Spatial dependence is conceptual. Spatial autocorrelation is something that you can actually see. You can estimate. It's an operational measure. Then spatial association is basically whatever you want it to be. It's usually the same as spatial autocorrelation, but it can also be used to refer to spatial dependence in a more general sense. It's not a rigorous term. It's often used in non-technical discussions or where you purposely do not want to be specific excuse me, about whether it pertains to the distribution, the full distribution, or just to a characteristic, a moment of that distribution. So spatial dependence, spatial autocorrelation, spatial association will focus on the autocorrelation. And to do that, we need to set the statistical framework. We need to set up what is the point of departure, what is the benchmark, what is the null hypothesis. This will obviously, as we already know, be spatial randomness. And where do we go when we reject spatial randomness? What are the alternative hypotheses to spatial randomness? First, let's think about what spatial randomness means in this particular context. Remember, in the point patterns, it meant something very specific. It meant basically that any point could land anywhere with equal probability. Now, how do we translate that into the pattern of the values observed at the locations? That's what we're focusing on here. So it's not the locations themselves, but it's what we observe at those locations. So it's not the coordinates of the centroid of the county, but it's the income of the county or the rainfall in the county that we are interested in. How is the patterning of those values? Is this spatially random? What does that mean? Well, it means that any pattern is equally likely as any other pattern. And we'll exploit this as we've done before. You can think of the data that you observe as a table. A table doesn't tell you where it is. So if that doesn't matter to you, then you can stick to non-spatial analysis and the table. Remember the very first lecture, the difference between spatial analysis and non-spatial analysis is that when you change the location, in non-spatial analysis it doesn't make any difference. So the average of our table will be the same no matter where these values land on our map. So if that's really the case, if it really doesn't matter where they land on our map, then they're spatially random. Another way to look at this, and these are differences between looking at the joint distribution, the whole pattern together, or looking at conditional distributions. How is the likelihood of observing a particular value at a given location affected by observing values at neighboring locations? Does it matter? Does it not matter? How does the unemployment rate in Champaign County relate to the unemployment rates in the neighboring counties? If there is no effect whatsoever, then we have spatial randomness. But if it turns out that high unemployment counties tend to be surrounded by other counties with high unemployment, and low unemployment counties tend to be surrounded by other counties with low unemployment, that's not random anymore. There's some structure there. And as before, what we'll try to do, it's always the same thing, we reject the randomness to move towards the structure. And there's two stages in here. First one is to establish that there is structure. The second one is to try to explain what kind of structure it is and why it's the way it is. And we probably won't get to that this semester, but maybe I'll talk about it a little bit at the very last lecture. So in a more abstract sense, when you have spatial randomness, the information that you have from your data, the information that you have, say, from the table of numbers that you look at, is the same irrespective of the map of those data. And we will exploit that by doing a permutation analysis. And we'll say, well, under spatial randomness, it really doesn't matter where the data end up. So I have my table, and I will just allocate these numbers over my map. That's a spatially random map. And then I'll do it again. It'll be a little bit different, but it's another spatially random map. And if we do this enough times, we get a sense of how some summary characteristic of the data will change when the data are spatially random. And then we'll be able to compare that to what we actually observe. It's the same technique we've used a number of times already. So this is the randomness. And it's really very difficult sometimes to tell whether a pattern is spatially random or not. And this, some of you may know this, Columbus crime data. This is the same table, the same numbers. But one of these maps is the real map, and one of these is a fake map. So in one of these maps, I took the 49 crime rates and just randomly put them in neighborhoods and made a map. And the other one is the true crime rates and how they look. Now, as it turns out, the one on the right is a fake map, the one on the left is the true map. And so our task is to come up with ways to be able to tell left from right, and to be able to say convincingly with a p-value, that's our ultimate goal, that formalizes the uncertainty of our decision, to be able to say, well, this is significantly non-random, and this is not. Now, one of the difficulties in doing this is that even in random patterns, and if we get around to it in one of the labs, we may actually try this out. Even in random patterns, you may think you see some clustering. And this is where the tests come in, because the tests quantify this. Your perception is very misleading. And we're, as we talked about when we discussed geovisualization, we're conditioned. This is how we're wired, to see patterns, to find patterns. So if we look long enough at this map, we will see clusters. Okay? But there aren't any. I mean, there are some there, but they're totally random. They're purely by chance. There's no systematic anything going on in that data set. Whereas here, if we see this high core of high crime in the center city, that is something that's highly unlikely to have happened randomly. And we can quantify that. We can say 1 in 100 or 1 in 1,000 of the random patterns that we might create would look like this. And so then we can make a decision and say, I'm willing to take that chance. If it's only random 1 in 1,000, that's not good enough for me. I reject this as a random pattern. This has structure. Now, it's not that easy. And what I've done here is taken some random numbers and in one case put them arbitrarily on the grid, and in the two other cases created spatially correlated patterns. One being more clustered than it would be randomly, the other one the opposite, more different than it would be randomly. And the one we will call positive spatial autocorrelation, the other one we will call negative spatial autocorrelation. The one in the middle is random. And you can actually do this in one of the labs. You create 100 random standard normal random variables, and you pull them in Geoda and make a grid map, and that's what you see. That's what this is. Then I put this through a spatial regression model to create negative spatial autocorrelation with the same random standard normal random numbers, and then I end up with a map like this, which is characterized by the checkerboard pattern. So the extreme negative spatial autocorrelation is black, white, black, white, black, white. Your neighbors are complete opposite of what you are. Okay? So obviously, when you have continuous data, it doesn't get that clear because it's not they're not two values, it's not binary, but there's a whole continuum. So it's a little more subtle. And in some cases, and it's more subtle even though on top of the 100 values that we have, we're also simplifying. In a choropleth map, it's like a histogram. We're simplifying this to, I believe, 6 different colors. So even though these may look more or less the same shade of brown, they may actually represent very different values, because the 100 values are grouped into what I forgot what it was exactly, but let's say 6 categories. So you only see 6 different values on the map. But still, relative to this one, maybe you don't see it, but if you pick out little parts like this with dark and light, and here again dark and light, you see many more of these, light and dark, many more of these than you would see in the random map. And that's the essence of what we're going to try to do is to put a p-value on this, quantify. How likely is it that we would see something like this when it's truly spatially random? And then the third one on the right is clustering of like values. And here again, you see all the darks being in the same spot and all the lights being to the right and near the bottom of the map. So there is structure in this map. Under spatial randomness, there is no structure. And here, this is very highly spatially correlated. If you want the technical details, behind each of these is a spatial autoregressive model. Autoregressive means I regress on myself, being the neighbors, and the coefficient that drives this process, in this case is 0.9, in this case is minus 0.9. Now these coefficients can be larger than 1, so this is about as high as extreme as it gets.